Sorry, it got cut, but we can start again. So just as there is a stress concentration factor for static loading, KT, there's a stress concentration factor for fatigue loading. And that factor is given as KF equals fatigue strength of notched specimen to the fatigue strength of notch free specimen. So clearly the notched specimen, the one which has the change in geometry, would have a maximum stress which would exceed the stress due to the notch-free specimen, the one which does not have changes in geometry. There's a factor Kf, which is defined for tensile loading or compressive loading, where there is sigma, and there is a Kfs, which is only defined for shear loading, where there's tau max involved or tau involved. Okay, so how do we go about computing this? Well, there is a empirical way in which people have computed this. There's something called notch sensitivity factor, Q. It is ratio of Kf minus K1, Kt minus 1, and the similar one for shear loading. The Kt1, Kt is the one we get for static loading. We've seen this before. There have been tables, I think it was table A15 in the book, in the appendix, which will give you KT. So once you have KT and once you know Q or QS, you can compute KF. Okay, so what you do that, you basically move around Q to the, well, you multiply both sides by KT minus 1 in this case, and you get this formula for KF. It's 1 plus Q KT minus 1, and then KFS is 1 plus QS KTS minus 1. Just these formulas written in a slightly different way. Okay, now that's fine, but how do you compute Q and QS? Well, KT and KTS are from table A15. So A15, appendix A15. So that's known. Now QQS, apparently there is a way to do this. This is another, there are figures which I'll show you, which will help you to get compute Q and QS. And then finally, it's just a matter of plugging it into the formula which I wrote down. So we've seen A15 before. I will not go through that. Let's look at how to compute Q and QS. Okay, so this is a figure which shows the notch sensitivity Q as a function of notch radius. Okay, so this is, by the way, divided based on the ultimate strength. So if you have specimens like steel, which is typically as a high strength, okay, so 200 kpsi, you look at that and then you will identify, well, based on the kpsi, the ultimate strength, you will figure out which line it is, then you'll figure out what R is, and based on the R, you'll compute the Q. This is the strength Q for tensile loading. There's another one for shear loading, QS, as a function of R. So again, you'll go and look at the ultimate strength, and then you will go pick up the right line, and then for the right R, you will pick up the Q. Okay, so that's how you compute Q. So maybe write it down here. Compute Q, QS. So once you've done that, you're ready to compute KFS. Okay, now there is also another way of doing this. If you don't like to keep track of this figure, the plot, this plot can be, you can write a regression formula. It's basically a curve fit Q to a function of R, right? If you curve fit, then you get this equation. Okay, Q is 1 divided by 1 plus square root A divided by square root of R. R is the notch radius, which is depends on the problem. And there's another constant here, though. It's called the Newberg constant. So if you know the Newberg constant, you can actually compute Q. Now, what would the Newberg constant depend on? There's a hint here. You can see that these lines depend on the material strength, SUT. So it clearly that the Newberg constant should depend on that SUT. So if you go here, it actually, yeah, so this basically gives you the Newberg constant, A, as a function of SUT. Okay, so why are there two formulas? This is if you're dealing with kpsi, use this the first formula. If you're dealing with MPa SI units, then use the second formula. It also tells you how to use it. A would be in inch half, half. Anyway, so once you get the Newberg constant, you can then use this formula number 2. You need to rearrange it a little bit, and then you get this formula for kf. Here, q has been eliminated, basically. So this directly gives you kf. You don't have to really go through q. You can just use the Newberg constant square root of a, and then r, notch radius, to compute kf. So maybe 3 is better than trying to go through the figure. So there's two ways of computing the stress concentration factor and fatigue loading. Now, these are formulas for bending an axial load. There's also formulas for torsion. We can probably there in the next page. Yeah, the torsion has these formulas. So it's just a sea of formulas. That's how it is. Some of these things are very hard to model. Fatigue, for example, is really hard to model. You really need to get into microstructure, and those things for a long time were, even now they are kind of hard to do, at least for a practicing engineer. And the way people deal with this is do a test, curve fit data, like example is this plot that has been obtained from an experimental database. Once you have these plots, you can make good predictions of how things will fail. Well, in this case, get the stress concentration factor and then predict it will fail or not. Okay, so now let's put all this to use. The new thing we've learned is that there is a stress concentration factor, Kf, which can be used in this way to compute the maximum stress. That's what we are interested in, which you want to compute the stress due to that particular notch, but in a fatigue loading.